Welcome to a read-along with Dr. Powell in the book Discrete Perspectives in Mathematics. This is subsection 5.4.3, primitive bit strings. So bit strings, meaning binary strings, strings of zeros and ones. Primitive bit strings are those that are not of the following form. So imagine this is a whole bit string, but we've put spaces in there so you can kind of visualize what is not making it primitive. It's made up of a repeating block. This one's made up of a repeating block. So we call those non-primitive. Primitive would be ones that are not made up of any smaller repeating block. Okay, so we're concentrating, at least in this example, on strings of length 36. Okay, so let's look at this diagram. These are factors of 36. Why would this be valuable for us right now? That's because it represents the different sizes of blocks we could have had. We could have a block of size 12 or 18, 4, 6, 9, 2, 3, or 1 for our repeating block. But we don't want to have those because we want it to be primitive. Now, let's look at this diagram. What's happening here? We're counting how many strings there are of size 36. Binary strings, not talking about primitive, just how many there are. There's 2 to the 36. How many bit strings of size 12? 2 to the 12th. How many of size 18? 2 to the 18, and so forth. How is this useful if we're just considering strings of size 36? Well, realize that the number of strings of size 36 that are made up of a repeating block of size 12 is actually equal to the number of strings of size 12. Because you take the number of strings size 12, so every string of size 12 can be related directly, but just by repeating it, to a string of size 36. So really, these are like, so this is the number of strings that of this length, of length 36, that is, that are made up of a repeating block of size 12, size 18, size 9, 6, 4, 2, and 3, and 1. Now, let's talk about primitive now. Primitive bit strings. And let's just look at the bottom right here. Let's just start from the bottom and think about what's going on. So this right here is the number of strings of size 2. So with 2 entries. This is the number of strings of size 1 with just 1 entry. There's 2 things, either a 0 or a 1. So what would not be primitive here? First, be made up of a repeating block. The repeating blocks of size strictly smaller than 2, the only option is to have a block of size 1. Notice that that's the only factor, 2 right here, that doesn't include itself. So we have a block here and a block here. So it could be repeating like a 0, 0 or 1, 1. Notice that these two, the 2 issues, are simply right in here, counted right here. So to find the number of primitive bit strings of size 2, all we have to do is take the number of strings of size 2, which is 4, 2 squared, and subtract that guy off, right? Subtract those because that's the number that we don't want to count, and we end up getting 2. Now, I'm going to build a little diagram here. I'm going to put a 2 here, and then what do I have to add to 2 to get that number? It's 2, which is precisely what is the result of this subtraction, right? So notice that 2 plus 2 is equal to 4. Now, over here, let's think about this. How many primitive bit strings are there of size 3? Realize that what we just counted here was the number of primitive bit strings of size 2. This is the number of primitive bit strings of size 1. Because everything of size 1 is primitive. 0 and 1, you can't make smaller repeating blocks. So there's 2 of those. Here, there's 2 that are not primitive, because that's what we did when we subtracted. And notice also that if we take what's primitive and what's not, we add them together, we end up getting the number of bit strings total. Okay, so now let's consider the number of strings of size 3. Now, strings of size 3, there's only the only size of repetitive block that you could have is size 1. And the ones of size 1 determine the 2 issues. You can't have 0, 0, 0, or 1, 1, 1, so you just have to take those off. So basically, to get this number, you add the number of that aren't primitive, which is what below, plus the number that are primitive. And you should get 8. So this should be 6. Meaning there are 6 primitive bit strings of size 3, 2 of size 2, and 2 of size 1. Now, let's keep going here and see. Okay, now let's do another one. What about this one right here? Number of how do we get the number of primitive bit strings this size? Notice that the number of primitive bit strings is actually turning out to be a summand solution in this case. 2 plus 2 was equal to 4, and 2 plus 6 is equal to 8. So let's see, using that idea, what do you think should go here? Let's see, 2 plus 2 plus 6, so everything below this point. So that's what, 8 and 2, that's 10, but we wanted to get up to 2 to the 6, which is 64. So it looks like probably going to have, we're going to have 54 would be the number. Let's see how that makes sense. So this is what we have left to add after we've already added the number of primitive bit strings of these. Oh, well, each summand itself is the number of primitive bit strings from the bottom. So inductively, if we say down below, like everything is primitive bit strings of these different sizes, you have to think that every single bit string is actually made up of a repeating block of a certain primitive type, or if you include a repetition of, if you also include no repetition, and it actually partitions all of these very neatly. So you just have to add all these up, and you actually get that value, or get the number of primitive bit strings at a particular place. So the number of primitive bit strings, let's see, of size 2 and 3 and 2, that actually gives you all the, if you just add these up, that gives you all of the issues that you don't want to have happen for something of size 6. So if you have a string of size 6, 1, 2, 3, 4, 5, 6, the different sizes of repeating blocks are, so you could have 1 or 2 or 3. Those are the different factors. And so now you don't want to double count anything. And so what you do is you say, okay, let's just take the primitives at the primitive number at each repeating block level. And then you're not double counting when you add these up, which is exactly what we get when we do a summand. So we have this, so we have the number of primitives that would repeat to have a repeating block of size 2, number of primitives of size 3, number of primitives of size 1. You add those up, those are the number of issues, take them off from 64, and you end up getting 54, which is the number of primitive bit strings at that level. Similarly, using a like idea, the summand solution at the top is going to be the number of primitive bit strings of size 36. Okay, so all we have to do is solve this summand solution. If we had a Mobius matrix for this, you'd be able to find that very nicely. In fact, but really it's simpler than that, because all we need to do is find the summand solution right here at the top. We don't need to find necessarily the summand solution in all these other guys, just the one right at the top here. That's the only one we need. So what we'll actually find is we'll have a simplified Mobius function that actually has output just one thing, which is summand solution at the top, which will actually help us out a little bit better. All right, so let's keep going and see how that's going to work, all right, as we move along here. All right, I mean, I need to clarify that just slightly. I guess the Mobius function will actually give you different, will enable you to find that at the top, but you'll still have to have a sum of things. All right, so let's take a look at this and consider, for instance, just solving the summand solution for this particular shape or particular post set here for different standard basis tuples. Like, why don't we just, take this one right here? What would the solution be? Well, notice in here we have a structure that looks like a power set, like a smaller power set right here, which is kind of what we get when we look at factorization post sets. It's actually locally, we can usually get a structure that looks like a power set. So here we have a 1, 0, 0, and a 1. Just look at that little piece right here. What would the summand solution be for this? Well, since it has the same shape as a power set here of where you're taking a set of size 2, just that little diamond, you'll end up getting something that looks like 1, negative 1s, 1 in this alternating pattern just in that little piece. Now, if you go outside this little piece, you're just going to have zeros because we've already kind of gotten everything together here. Notice that everything below this point right here is 0, sums to 0, and this one as well. And so we just need to concentrate on the pieces that look like a power set structure and just put on 1s, negative 1s, and 1s, especially if we have a 1 on the bottom here as we go up and look at that certain type of solution. So for instance, let's take a look at this. Notice we've kind of circled a few things here. Right, okay. Okay, so notice we're talking about surviving to the top, all right? When will non-zero entries in the solution make it to the top? I mean, notice that this non-zero entry actually contributed nothing to the top summand solution. It's always going to contribute a 0 from here. So you don't even get anything escaping to the top because of the power set structure that's right locally around it. So in fact, notice that this guy right here, right, is with a 1 here and 0s here. It will contributes nothing to the top. That's what we just saw. By symmetry, this contributes nothing to the top. This one contributes nothing to the top because of a power set structure right here that it's in. There's a diamond shape. Similarly, let's see here. Oh, this is, if you had a 1 here and a 0 here, that's just a singleton set power set, and that won't escape to the top. And so, and similarly over here, the only ones that actually escape to the top. So let's see, as we go along, okay. Remember, we're interested in the summand at the top. Okay, right, so we're trying to get up there. So we only need to consider the structure tuple cumulative sums that look like this at the way top. Okay, so just this one right here. Everything else, we don't have to worry about. It's just this structure right here, because everything else will have a summand that doesn't quite make it to the top. All right. So for this one right here, let's just consider this structure. All right, so, well, this guy where you have a 1 at the top, that's just going to give us a 1. Now, what does this mean? This means that if you take the list of cumulative sums, you take the entry that corresponds to the top, and you're going to be multiplying it to this guy, which comes from the top. It's the solution with a 1 at the top, right? When 0's elsewhere. And so 2 to the 36th power is going to be the contribution to the top summand. So 2 2 to the 36 times this solution here, just get, or at least, but we're only concentrating on the top node. So 2 to the 36 times the 1 at that node. Now let's go to this one right here. All right, there's a 1 right here. And okay, and its solution is 1 minus 1, so it's contributing a negative 1. So the guy right here will contribute a negative 1 to the top. So the guy right here was 2 to the 12th. So 2 to the 12th multiplied, so 2 to the 12th is going to be multiplied to this solution right here. So the top, it'll contribute a negative 1 times 2 to the 12th to the top. This over here has a solution of a negative 1 on the top. So this corresponds to 2 to the 18th. So we take 2 to the 18th times that negative 1. And now in this position, it contributes a 1 at the top. So we're going to be saying 2 to the 6 times that 1. And then we're adding up the solutions, like so, just like we add up our columns with things multiplied to them in the matrix in order to evaluate it. But we're only focusing on the top entry of that column right there and there and there. And so we just take those cumulative sum numbers and multiply it to that guy, to that guy, to that guy, to that guy, but just at the top and add them up. And then we end up getting the result. So 2 to the 36 times E1 to the 2 times the, so we take this right here, right? That's in the domain. Okay, this is what's in the domain. And then it has solution. Well, let's see. These are the different solutions. So we're multiplying these guys to the different solutions and adding the results to see what the solution would be at, right? Because why did we ignored everything else down below? Because they don't contribute to the top. So because we're just focusing on the top. So really this isn't quite right if you want to get the full power set solution, but it is equal, but it will give you the top solution because these guys are actually like the 1, negative 1, negative 1, 1 are the same as it would be in the full power set solution from cumulative sum to sum ends. So basically we just get that, we just can add in the tops and add that up, and we end up getting the number of primitive bit strings by doing so. So it's kind of like, it's inclusion exclusion is what it is. We have all the strings, then we take away ones that have blocks of size 12, ones blocks of size 18, but then we have to add back in what we had an overlap with this one and this one, blocks of size 6. That's the overlap, because those could contribute to this one or this one. So it's kind of like, so we could have a little diagram here. So we have bit strings of size 36. We have bits, okay, we have ones that are made up of a repeating block of size 12, ones that are made up of a repeating block of size 18. And they overlap right here with ones of size 6. So what we need to do is we need to take out this clump, and we take out that clump, we have the primitive bit strings. Now, how do you get the size of this clump? Well, you have to add 12 and 18, or the number of size 12, so 2 to the 12th. So you have to add 2 to the 12th plus 2 to the 18, but then you have to take away what's common, which is 2 to the 6. And that's what you're taking away from that. So when you take this away, it changes all those signs, right? And so you end up getting, it's just a simple inclusion exclusion thing. But the point of this little argument that we're going through is we're developing a function, and we're going to use this symbol here for it, the Mobius symbol. We're developing a function that'll actually give us this inclusion exclusion without any thought. It'll just kind of give it to us immediately. Okay, so that's kind of where we're headed with this. All right, so this kind of walks through a little bit about what we were just talking about above, and this idea right here. and looking at finding power set structures inside. Now, what we need is we want to use this, we want to have a function here, a Mobius function on integers, which is going to give us the plus minus information dealing with that we want as we keep on looking at the top here. All right. So this is the definition. We'll talk about it. 0 if n has a square factor. Okay. Now let's think about what that means here in this diagram right here. Let's go back up to the factors of 36. So where to put a plus or minus? We want it to be 0 when there's a square factor. What we're going to be doing is we look at this whole diagram and we're going to like flip-flop it a little bit. We're going to divide everything by 36, or kind of look at what's left to multiply to get 36. Notice that 9 times 4 is equal to 36. 6, okay, all right. And let's see, let's do 4. 4 times 9 is 36. 2 times 18. 3 times 3 times 9. Excuse me, 3 times 12, sorry, 3 times 12, and 1 times 36. So notice that all of these guys right here actually have square factors. That's okay. These have square factors. Well, let's think about factors for a minute. Each of these numbers can be thought of as, so this is of what's left to multiply, right? Okay, and what's left to multiply here, let's think about that. What's left to multiply here is 6, here it's 2, here it's 3, and here it's 1. Think of this as a power set kind of going down, and think of each of these as like lists of factors. So here, this is like the empty set. This is like a single factor of 3, a single factor of 2. This is like factors of 2 and 3. And then here, what have we added? We haven't added any new factor. We've just taken this guy right here and said 3, 3 into like a multi-set. Well, a multi-set like that doesn't really fit into a power set structure, so it's going to be ignored. And that happens when we're just putting in extra factors that we already have, which is equivalent to saying square factors. If we take 36 and we divide by that node, that says that's something outside of a power set structure. And why did we take 36 divided by the node? That's because we wanted to get a power set structure that was focused at the top. So to get one at the top, we're going to have a power set structure facing down, because power sets in themselves are very symmetric. They're the same up as down. So we may as well start down and we'll get the same kind of feel for it. So here, in order to isolate this and get rid of everything that's outside of it, we just take out things that have square factors when we take 36 divided by that guy. And then we'll just be left with the power set structure right at the top. Okay, so that's kind of what we're going to be doing. We're kind of doing an ignoring type thing in order to make that look and act right. Okay, so let's go down here and see where we're at. So I see this -1 to the k. That comes from alternating levels from power set structure when we're looking at the Saman solutions. So k, what does that mean? So when there's, it's the number of distinct prime divisors, so like the size of the subset. So if the subset is size 0, we're always going to have a 1. So there's always a 1 at the top, because we kind of make the top when we divide out as being like the empty set, or like size 0. Kind of make that as size 0 at the top here. So a size 0 at the top. And so, and then here's size 1. So then it'll give you the negative ones and the ones. So it'll be a repeat. It'll be an alternating pattern where we're starting with a positive 1 on the top. And so that's where that comes into place. So this little function right here actually tells us exactly how to put the pluses and minuses on if you're just looking at the factorization post set of 36. So we got to flip the post set upside down by saying 36 divided by the different factors. And that's what we plug into this Mobius function. But then times, of course, the guy that's at the top, which is just the 36 itself here, the 12 itself. So the 12 appears here in the denominator and here in the exponent. So denominator and exponent, those guys will be the same. Okay, so right here, this one is the same as that. That's the same as that. And that's the same as that. Okay, as those exponents. Okay, so using this definition, this is the Mobius, this arithmetic Mobius function here. Using this definition, we can get our pluses and minuses, because this is mu of 1, and notice mu of 1 is, well, it's negative 1 to the 0, which is just 1. Here, this is negative 1 because we get 36 divided by 12, which is 3. And that housing has 1 prime factor, so k would be 1. So so negative 1 to the 1 would be negative 1. Here, let's see, 36 divided by 18 is 2, which has only 1 prime factor. So that's negative 1 to the 1, so just negative 1. Here, this is 36 divided by 6 is 6, which is 2 prime factors. So it's negative 1 squared, so just positive 1. And so we end up getting exactly what we desired, that minus that plus that. Okay, so let's look at an example here. Let's find the number of primitive bit strings of length 60. So we're going to look at the top of the post set structure that's of size 60, that's right here. It's isomorphic to 2, 3, 5, the power set on the set 2, 3, 5. How did we get that? Well, because 60 divided by 12 is 5. 60 divided by 20 is 3. 60 divided by 30 is 2. Isomorphic just means it has the exact same structure as, just a relabeling difference here. Okay, so we get something like this, and we're going to be turning it upside down, going down here. We're going to have the Mobius function. In fact, you can get what the Mobius function will do just by looking at the post set. You could either follow this rule right here, or if you had the post set handy, you actually know exactly what to do. 1 here, negatives here, pluses here, minus there, done. And then just ignore everything else that's outside that little post set structure. So the factorization post sets are not are not power sets structures, but they have power set structures inside of them, because when you repeat factors, you get things out here which don't contribute to a solution up here. Okay, so we can see that right here. Now, as we go, we get this. In fact, why don't we just try it and see what happens? So here, if we divide everything by 60 in this post set structure, you actually see you have a 1, 5, 3, 2, this right here. So you actually notice that when you run this into the Mobius function, 1 prime factor, right? So what do you get? You get a negative 1, because you take negative 1 and raise it to the so take negative 1 and you raise it to the first power. For this, on this line, you take negative 1 and square it. This one, you take negative 1 and you cube it. So even if you didn't have the post set diagram handy, or you didn't want to try to figure out this Hasse diagram here, then what you do instead is you can just use the definition of the Mobius function as is and just factor each thing you're plugging in. And it makes it nice.